Hey everybody, how's it going? You good?
Is the
Awesome to
elevator
see you.
music standard for this?
No, I was just kind of making a joke about waiting rooms. Hmm. Let's take some attendance here. Thank you all for showing up on time. I appreciate it. Oh, let's see. Ella's here. Kodiak is in the waiting room and coming in. Michael's here with a great NASA shirt. I appreciate the worm. Anne's here. Gwen is here. Marshall's here. Alyssa's here. Aiden's here. Kat's here. Am I missing? Oh, Elijah's at the dentist. That's what's going on. Okay. Caitlin is here. Grayson thinks they're not in this class, but I'm still on my roster for some reason, so I'll have to revise or go back to that. Anthony is there. Josie is there. Perfect. And Julia. That's everybody. Hi, everybody. Good morning. How'd your first class go? Kind of meh. All right. Well, let's see. Let's take a look at this. My attendance is done. That's excellent. I'm recording myself for this class. Not you guys, just my own video. So what I'm going to try to do for anyone who misses this class, or if you want to come back and go over it again, I'll post it on our classroom. What I'm going to do is I'm going to try to repeat chat messages and questions you have out loud. Grayson doesn't go to school anymore. I see. Understood. Perfect. Good to know. But yeah, I'm going to try to repeat your questions out loud into my mic so it gets recorded into our actual thing. Gosh, I really hope it's recording my sound. Cross your fingers. If it doesn't, then this could be a disaster. And I'll just record another video for this. I have my notes here, so I can always record a new video. All right. So today I want to give you like a historical introduction to the atom, the structure of matter, and people's thinking about that, and how thinking has changed over time. Not going to be any homework this week. I think I'm going to give my first homework for you guys on Monday next week, because I feel like, the first week of school, you got enough going on. So hooray for that. But I also know that like a lecture like this can kind of get pretty boring if that's all we do. So I'd love to make this into more of an interactive conversation if possible. So if you have a question or something to say, just blurt it out. I'll try to pause to get your guys' reactions to certain things. And I'm going to try to talk you through some of the history of the atom and how people have thought about matter throughout history. So I guess the first thing to talk about is like, what is matter? When I say matter, for me as a physicist, I'm talking about something very specific. Does anyone have any ideas of like what matter is?
Stuff that makes stuff.
That's genuinely not a very bad definition. Stuff that makes stuff. It is really hard to define. I think the word stuff is kind of the best we can do, unless you want to get really, really technical about it. Matter is, well, actually not everything. It's everything us and that everything we interact with on a regular basis. But if you look at the composition of the universe, technically, according to some crazy astrophysicists, most of our universe is not matter like us. It's other stuff like dark matter, which we don't know what it is, and the even more mysterious dark energy, which seems to be responsible for the accelerating expansion of the universe. Kitty cat! Sorry, I get distracted by kitty cats. They're very cute. So, yeah, it's like, I'm trying to remember the exact proportions. I think 70% of all the stuff that makes up the universe is this mysterious dark energy thing that we have no idea what it even is or where it comes from or any of its properties. And like another 15, 25, something like that percent is this dark matter stuff, which we have some ideas about and we're really trying hard to figure out what it is. And then, a few percent of the universe is the stuff that makes us up, matter, regular, and a physicist would call it baryonic matter. So
a quick, maybe probably not precise Google search says about 68 for dark energy, 27 for dark matter, and then 5% for everything.
Yeah, that's about right. Everything else being us. So the stuff that makes us up and the stuff that we interact with every day is actually by far the minority of the real stuff in the universe. Despite that fact, it is going to be the entire focus of this entire class is regular matter, the stuff that we're used to. And I don't think we're going to talk about dark matter or dark energy ever again in this class unless I get onto one of my things and start going crazy. So, matter is stuff. In physics, you'd learn that matter is kind of, in some odd ways, interchangeable with and the same as energy. Again, not super important for us. If we start transforming matter into energy in our chemistry class, I have bigger worries. For example, us turning the entire science building into a giant smoking crater because we've made a nuclear bomb. Which I think we technically could do. I don't know if we have the uranium to do it, but we probably have the tools to do it. Isn't that fun? But probably not going to be doing that. I hope. We might do some thermite or some other fun explosion kind of reactions, but we're not going to make a nuclear bomb or anything like that. I know. That's a big disappointment. We were all hoping for it. Anyway, so matter is just the stuff that makes us up. And I'm sure you guys have heard a lot about atoms and subatomic particles in your previous science classes, 6th through 9th grade, yeah? So can anyone name some subatomic particles or bits of matter that they know about? And we don't have to have the same people always talking. It'd be nice if a new person volunteered. If not, I have this little 20-sided dice that I will roll and choose you at random to volunteer a bit of matter you know about. Oh, I know, terrifying.
That just Pokemon-like thing. Bishop, I choose you.
Yeah, something like that. All right. Well, we don't need to do it right now. We're going to mention all the subatomic particles we need to know about later on today. Okay. So, in modern theory, so I guess the original idea, I should say, of an atom, which is what we're talking about today, is that it's the smallest indivisible unit of matter, of stuff. And there's some really interesting philosophical principles that go along with that idea, that there is a smallest indivisible unit of stuff. You'd have to read the ancient Greeks and the ancient Indians to really get into this, and I don't want to get into it right now, but the existence of a smallest indivisible unit of stuff kind of implies that everything else that's not stuff is what they called void. Modern physics would probably call that empty vacuum, which does exist. And there's a couple, problems with this idea of atomism, that it's indivisible. Excuse me. The modern idea of an atom is actually quite different than the ancient idea of an atom being some indivisible fundamental unit of stuff. Because as we know, in, modern sense, the word atom means something very specific, and that thing is not indivisible. There are parts of an atom, which we're going to talk about today, all the parts of an atom. So I want to just go through some of the history, because I love history. It's one of my favorite subjects. But I want to go through some of the history of how we got to the modern concept of atomism and atoms in general. The earliest thing I can find about referencing anything like atoms, so some smallest indivisible part of matter that makes everything up, is this guy Aruni, who's a Vedic sage in, I think, 8th century BC, India. And his theory was that everything is made of these particles that are way too small to be seen, that mass together into the substances and objects that we experience, which is a pretty interesting idea for something, 2,800 years ago. And I guess there's this guy who evolved from that maybe 100 years later. His dates are very uncertain. So what I found was he could have lived anywhere from 600 to 200 BCE. His name is Chem1AtomsLive, which I looked it up. It technically means atom eater, which, we're all atom eaters. I mean, if you're eating something other than atoms, I'm super concerned about you. And, tell me about it so that, you could go win a Nobel Prize, because that's interesting. But yeah, atom eater. And I found out about him pretty recently, and I really want to read his text, because it looks super interesting. There's some really interesting parallels to modern physics and chemistry. So he theorized that everything is divisible, but the division can't go on forever. There's a smallest unit, which he called Parmanu, which I think is Sanskrit. But the smallest unit that can't be divided. It's eternal, and it combines in different ways to make complex substances, which is some really fascinating parallels. If you look into other bits of his philosophy, he's one of the very first ancient physicists, really. And very much like the Greeks, the Indians were sort of thought experiment, not physical experiment kind of guys. But if you look into his theories, there's a lot of interesting parallels to Newton, to modern thermodynamics, and even quantum physics kind of stuff. So that's something I personally would love to look into more. And I'm sure there are other ideas out there across the world about atomism. Problem is, most textbooks and most history books focus on the Greek and Western tradition. So I thought it was interesting to bring in the Indian tradition there, which is actually technically a bit earlier than the Greeks. Earlier, or maybe around exactly the same time, actually. Because the Greeks, the classic Greeks that we think about when we think about atomism, are Leucippus and Democritus, around the 500s to maybe 600s BC. And they talk about atomism. There's nothing that survives of Leucippus other than the fact that he taught Democritus, and the ideas maybe originate with him. There's some theorization that these ideas from India were a little bit earlier, and they could have migrated over to Greece. Really hard to prove, because none of these original texts survive. Even Democritus, none of his texts survive, although apparently we know of, from other references in ancient works, 80 or more texts that he wrote. And we have fragments of Democritus and other people writing about what he wrote. But he is credited with the first use of the word atom, or atomos, which is the basic undivisible unit of matter in his sort of cosmology, his theory of how things worked. So we at least do owe the word atom to Democritus, although we ought to also recognize that the idea of atomism does not start with just the ancient Greeks, as most, including our textbook, would have you believe. And then the idea is kind of, it's hard to follow up on, right? Because it's a really interesting idea, but in the ancient world, how in the world do you experiment with atoms, right? They're so tiny, it's almost impossible to prove at that point. You need some very significant technology, 2,500 years worth of technological development before you can actually start thinking about experimenting with atoms. 2,200, whatever. So the idea kind of goes underground. There's some history of it in the medieval world. If you want to look that up, it's kind of interesting. Across the world, in the Islamic world, in the European world, still in India, there's some sort of thread of atomism going through things, but most of history and most of intellectual endeavor kind of follows Aristotle, who rejected atomism, that there's this indivisible unit of stuff that makes things up. And he said that there are really only, everything is made of these continuous substances, fire, air, earth, and water, and everything is some combination of those. So I remember reading Aristotle when I was a senior in high school, and I remember him talking about how steam is some combination of air and water, but it's mostly air, and so it rises into the sky because it wants to be with the rest of the air, and some kind of crazy stuff like that. Or that a stone is earth, and it drops to the ground because it's mostly earth, and it wants to be with the rest of the earth, and you can never teach a stone to fall upwards. Which is true, you cannot teach a stone to fall upwards, but it's not because it wants to be with the rest of the earth. Aristotle had some really weird ideas. I think it was Aristotle who asserted that flies only have 4 legs, and everyone in history believed him for like 1,000 years until anyone bothered to look. I mean, it's pretty obvious. You can go get a fly and see that they don't have 4 legs. But because Aristotle was such an authority, I guess everyone just believed him for like over 1,000 years. And it's kind of the same with the elemental stuff that he talks about, all this continuous fire, air, earth, and water. It is kind of interesting to think about, I'll look at, a candle, and Aristotle would say, okay, it's mostly made of earth because it's this solid substance, but you can set it on fire, so it has some fire essence inside of it somewhere. So it's kind of funny to think about, all the different combinations that he would talk about. So yeah, Aristotle kind of dominates the conversation for a long time. Somewhere in there, I think it's around the 1600s, is this idea of, I'm going to have to look at this word and pronounce it correctly. It's corpuscularianism. Yes, I actually got that right. Corpuscularianism. Corpuscles, which is a sort of vaguely filthy sounding word, are just sort of these little, I think it really means little bodies unto themselves, which is kind of linked with atomism. It's the idea, like I said, I think it comes around in the 1600s, as far as I can tell. It might be earlier than that. I just can't find the historical references. But, you know what? I might as well spell that for you guys because, oh my God. You ready? Corpuscularianism. Whew. Okay. So corpuscularianism is the idea that matter is not these continuous substances, elements of Aristotle, but it's just little things. And corpuscles, I guess technically, if you look into the roots of the word, are little bodies, not like human bodies, but like bodies of stuff. It's not exactly atomism because corpuscles are able to be divided. They're not indivisible, but they are sort of the building blocks of stuff. And I don't think it was super mainstream. It's linked with alchemy. For example, like corpuscles of mercury would get into substances and change the nature of other like metals, for example, and turn it into gold. Isaac Newton, who is a physics sort of founder, basically when he got into his 30s, he quit doing physics altogether and dedicated the rest of his life to alchemy, and was kind of crazy. Spent most of his life trying to find the Philosopher's Stone, which you probably all know from Harry Potter, right? It's an actual thing Isaac Newton tried to recreate, which is always insane to me that he gave up. He did all of his physics work in his 20s and early 30s, and then dedicated the rest of his life to alchemy, trying to make gold out of lead and trying to find the elixir of everlasting life. Which I guess back in the 1500s, 1600s, that was like a thing still. So, it feels like a very different world than today when we try to do that with, pharmaceuticals. Okay. And I have plenty of crazy stories about Newton. If you read any of his book on optics, he experiments with how his eye actually sees things by taking a blunt, dull knife and sticking it between his eye and his eye socket and just like moving it around and seeing how it changes. Kind of disgusting. In physics 2, when I get to that, I read it out for everybody and it's like, but I read out the original text. Yeah, but Newton was kind of nuts, which is fine. Most physicists are. I think I would include myself in that. Anyway, let's get away from alchemy. Although alchemy kind of is the beginnings of chemistry, this class. So I'm sure I'll mention it again. All sorts of crazy stuff going on with alchemy. Okay. So in the 1660s, Robert Boyle, who's a famous, very early chemist, published a book called The Skeptical Chemist. And I want to spell this for you. I'm going to put it in chat here. Because I think the spelling is kind of funny. Early English spelling like that in the early 1600s is just hilarious. Because they hadn't really settled on how to spell English words at that point. Modern English anyway, was still a new language. So all the spellings are kind of crazy.
Kind of phonetic.
Yeah, yeah, exactly. But in that book, the Skeptical Chemist, he espoused a version of atomism because of some problems that arose directly from his experiments with really basic chemistry, stuff that's way more basic than we're going to do. But he was one of the first to bring the idea of atomism and atoms back into the mainstream. And this is kind of, after Boyle, is kind of where most textbooks, and I think our textbook even, pick up the story of atoms. Everyone seems to love to start the story with John Dalton, who is I think an English physicist. 1808 is the date usually given for his papers. And he accepted the ancient Greek model from Democritus of atoms being the smallest indivisible unit of matter. He wrote a lot about it, and no one's really sure where he got the idea from. Some people think it came from his experiments with gas laws, which we're going to get to experiments with gas laws way later in the year. It might be the last thing we do. It depends on how fast we go. But yeah, gas laws are really important. So he was doing those experiments in the early 1800s. There's also some assertions that he totally plagiarized the ideas from some other guy. And there's debate about whether that's true or not. Knowing scientists, maybe not that unlikely. The ones who get famous, anyway, tend not to be the most ethical people. But some of them are nice. So 1808, that's when sort of this idea of atoms really comes back into the mainstream, especially from an experimental perspective. And really, when we want to start talking about real experiments that start proving the nature of atoms, we have to go about another 100 years forward. Thomson discovered the electron in 1897, for which he won a Nobel Prize. Through some experiments, we don't really need to go into them right now, but the important thing for atoms is that a few years later, in 1904, he came up with what's called the plum pudding model of atoms. And you know what? It would be useful right now if I could share my screen with you, and I can draw out the plum pudding model. Oh dear. Where is the thingy thing? I have lost it. Oh boy. There it is. Okay. Just had to reload. Okay, I'm hoping you all can see my kind of little whiteboard kind of dude here. I'm going to get my tablet out, and we're going to do some drawings. So, this is Thomson's plum pudding model of the atom. So he had just discovered electrons, and he knew they were negatively charged. So, by default, I'm going to use the E- for electrons. And kind of what he thought that an atom was is this sort of electrons just kind of hanging out all together. And in order to neutralize the negative charge, there was just this sort of vague, nebulous cloud of positive charge hanging out in the middle to make the atom neutral. Because most atoms are electrically neutral. Anyway, the ones we usually work with. If they're not, you're going to get a big shock. Literally. So this plum pudding model is that like there is pudding, which is the positive charge, and the electrons are kind of like plums embedded in it. Some people go like a fruitcake model, where there's like bread, which is the positive charge, and the electrons are like little bits of fruit embedded inside of it. Pretty quickly, people realized that this could not be true, and through experiments, 1911. So you know what? I might as well put up. This is 1904. Thomson. But pretty quickly, people realized through experiment that this is not correct. Rutherford, Erford, apologies for my atrocious handwriting, 1911, does some experiments, some really interesting experiments with gold foil. So what he does is he gets positively charged particles. Who knows what they are? They're just some positively charged particles, and he shoots them at really high speed at gold foil. So there's a bunch of gold. There's the chemical symbol for gold. And he measures where these charged particles go once they hit the gold foil. And what he realizes is that most of them kind of pass through. Maybe some of them are like deflected a little bit. Some of them scatter a little bit. But every once in a while, he gets one that bounces straight off in the opposite direction. And if the atom was this sort of just cloud of positive charge, you'd expect it just to go straight through, or maybe sometimes get deflected. Maybe when it passes close to another cloud of positive charge, the electrical forces will curve its path, right? And you'll get something like that. But it shouldn't bounce off. So what he concludes from this is that the positive charge in an atom is concentrated all at the center, all in the same place, and it's this kind of solid thing. And he calls this the nucleus. And I'm sure this is a review for some of you. I'm hoping, anyway. But it's a good review to have. And actually, if you do this experiment really carefully, and you do the percentages, you can actually figure out how big the nucleus is. Just by, like, the percentage of things that bounce off versus the percentage of things that go straight through. But what he concludes basically is that an atom is, and I should not have put a dividing line there because I need to draw a little bit more. He concludes that the atom is this nucleus, which is positively charged, and electrons sort of going around it, just hanging out around it, sort of randomly. Which is getting closer to our modern, idea of the atom. All these developments are coming pretty fast because just a couple years later, 1913, Niels Bohr, really famous physicist, 1913, there we go, does some more experiments, and they're very, very complicated experiments, but they have to do with something called spectroscopy, which is one of my favorite specialty subjects that I used to study a lot. But what he concludes is that, okay, there's this nucleus. At some point, people discover protons in the nucleus and neutrons, and we'll talk about that. But the important thing is that electrons aren't just hanging out outside the nucleus. They are in these little orbits. They orbit around at very particular distances. So electrons only exist in really what he calls quantized energy levels. Anyone know what the word quantized means? Because it's going to be really important. I'm going to resize my window here so I can see. I'll use quantized. I'm going to write it down so you can write it for yourself too.
Something like there's a specific number and a specific.
Yeah, it kind of means that there are set, in this case, levels of energy that electrons can exist at, and you can never be in between these set levels. And this idea is really the beginning of quantum mechanics. Hooray, quantum mechanics. You can see where that root of that word comes from, quantized. It always annoys me when like TV shows or something mentions a quantum leap forward, because actually a quantum leap would be extremely small. I mean, the leaps between energy levels here are very, very tiny. In fact, the smallest unit. So when they're trying to talk about something like a huge leap forward in technology and they say, oh, it's a quantum leap. No, not really, guys. It's more like a real big leap. I don't know. Come up with some other fun word for that. But anyway, yeah, Niels Bohr in 1913, this is really the beginning of quantum mechanics. And I think it's worth it to talk about how he did this kind of experiment. Because I'd like to do, later on in the year, I'd like to do something kind of like this. We have some of the materials to do, not exactly his experiment, but something a bit more basic and easier to see, I think. So what he does, and what we're going to do actually, is we have these little gas tubes. They're like little glass tubes that are narrow, and on the end they have these metal caps. And inside this tube, it's been pumped out to a vacuum, and then they fill it with, I don't know, for example, hydrogen, some gas that you know about. And you put it into this little, it's basically a fluorescent light bulb. You put some electrical current through it. These are called gas discharge tubes. And you put some like high electrical current through it, and it just pumps up these electrons into higher energy states, and then they will fall back down into lower energy states. And what Bohr kind of discovered is that if you measure the light coming out of this, so here's like a graph. This is, I don't know, the vertical axis is like, let's say how much light there is. So I'll say light intensity, I. And then this bottom axis, the x-axis, is going to be wavelength. In physics, we use a Greek lambda for wavelength. If you have the same element or the same gas, like hydrogen or helium or, I don't know, nitrogen, if you have the exact same gas, it always produces the same pattern. So, for example, some particular gas might have really strong light coming out of that particular wavelength, and maybe like a little one here, and a medium one there, and a big one there. And every time you have, like, let's say just for example, let's say that this is hydrogen, although that's not what hydrogen spectrum looks like. But every time you have hydrogen in your gas tube, it makes this exact same pattern at the same wavelengths. You know, you can measure these wavelengths. And the intensities scale too. But these same wavelengths appear over and over again for the same element, no matter what you do, as long as it's a pure element. So what Bohr figured out was that this wavelength of light coming out of that that tube, that really hot gas, comes from these electron orbits. So let's see, here's our nucleus. I'm going to really try to draw this carefully so it's not as messy as the one over here. Let's say let's make it really basic. There's 3 orbital levels. So the lowest one here is the least amount of energy, then the middle amount of energy, and then the highest amount of energy for these electrons. And they can only exist in these 3 orbits. So let's say because we're running electrical current through this gas tube, our electron is way up, hanging up here. He's got a lot of energy. It's getting energy from the electrical current. And then he spontaneously, just randomly, decays down to this energy level, the lower energy level. The difference in energy between this top energy level and this bottom one, it transforms exactly to the wavelength of light it emits, which I think is pretty cool. And so what Bohr realized is that because these exact same wavelengths always show up exactly the same way every time, that what's going on is that these electrons are only going between very particular well-defined energy levels. So for this really simple atom I've drawn, let's say there's this upper level, it could transition from this upper one down to the middle one, which would produce a particular wavelength of light. And then it could also transition from the upper one down to the lowest one, which would be more energy difference. So probably bigger, smaller wavelength, I should say. And they could also go from the middle one down to the lowest one. And that would produce a separate one. So a spectrum of this guy might look something like, depending on how we're doing it, it might look like, there's a little peak, maybe there's a big peak, and there's a littler one again. And what Bohr would have realized is that, okay, so in this element, there are 3 energy levels, and, the sizes of the peaks correspond to how likely that transition is. I know this is getting pretty abstract, isn't it, guys? I should take a break for a second here, right at the end of the Bohr model. How are we doing so far? You can give me a thumbs up or a thumbs down or some thumb in between. Oh, good. Excellent. And I'm sure you guys have seen most of this before, right, in your previous science classes? Excellent. Excellent, excellent, excellent. Okay. So for the most part, this is what we're going to be talking about. This kind of model of atoms with energy levels and electron orbitals. This is what we're going to be talking about in this class. There is some more progress, however. I'm going to make a new thing here. There's some more progress to be made. 1926. Really, this is the start of real quantum mechanics. A guy who you may or may not have heard of, Erwin Schrödinger. I think there's an umlaut there. Erwin Schrödinger does some interesting, very complicated experiments and figures out that, this idea of electrons in discrete orbits where they're actually physically orbiting like little planets, not quite correct. The energy levels thing is probably right. But he figures out that, okay, there's this nucleus with protons and neutrons and stuff. It's positively charged. But then electrons are kind of in this nebulous cloud, and you can never actually quite find out where they are. They're kind of just hanging out. And they're spread out like, instead of an electron being like a little marble that orbits around, it's more like a butter that's spread out over a bunch of toast. Boy, that's a weird analogy, you guys. I can't believe I made that analogy. Electrons are butter. But that is kind of the foundations of quantum physics. And you know what? Thankfully for all of us, we don't have to go into quantum physics. Hooray. If you do want to get into quantum physics, take Physics 1 and then take Physics 2. Because Physics 2 is really where, at the very end of Physics 2, if we have time, is where we get into it. Okay, we're like 45 minutes into class. How are we doing? Just want to do a check-in. It's been a hell of a lot of information to throw at you. We got 15 minutes left. Okay. So that is really all I wanted to do for the history of the atom. Is there anything someone would like to ask questions about? Anything anyone would like to add to this? Anyone know anything else about atoms or subatomic particles before we move on a bit?
Why do we use the Greek symbol for the wavelength?
You know what? It's a great question. I think it's just the way it always has been. You will find that scientists of all stripes, and especially physicists and chemists, and in my case, astronomers, really love to not change things, even if there's a better way to do it. I don't know. Another way to think about it too is that I looked through this once, we've used every letter in our alphabet like 6 different times over to represent things in chemistry and physics. So we kind of needed a new alphabet to start representing things. And now we've used the Greek alphabet so much, like every letter in the Greek alphabet so much, that we've kind of used those like 6 or 7 times over each as well. So it gets confusing, especially when you take physics. I try to be really good about, when we're doing physics stuff, to say, okay, this time L means angular momentum and not length or something like that. But yeah, it does get confusing when multiple things are used multiple times. Like the letter M is used for mass, but it's also used for so many other things. It's kind of ridiculous. Yeah. And I guess the best way to get around that or to navigate that is you have to develop a sense, and it takes time. I wouldn't expect you to do it instantly, but it takes time. You develop this sense of like, okay, today I'm working with, say, quantum mechanics. So the variable L means this particular thing. Whereas if I was working with rotational motion, L would be a completely different thing. Yeah. Or, the letter lambda for Greek, or delta or something like that. They all have different meanings in different sort of subfields. And physicists, boy, do they really physicists and chemists love to use variables for stuff like that. Okay, if there's no other questions, then let's really, really quickly just go through the particle zoo, and not all of the particle zoo. Hooray! So we've talked about electrons. Electrons are negatively charged. Negatively charged. They're very small mass, but they do have mass. What else? As far as we can tell, they have no size. They are a perfect geometrical point, which is a really weird concept. I'm not really sure how something that has mass can have no size. But then again, if you could figure that out, then I think you'd probably win a Nobel Prize pretty much instantly. So maybe work on that. I don't know. And electrons are these guys that are sort of in a cloud surrounding the nucleus. But then, separate from them, there's the nucleons. Probably the most important of which is the proton. I'll call it a P+. Proton is positively charged. And I guess one of the cool things about that is that the amount of positive charge on a proton is exactly equal to the amount of negative charge on an electron. So they totally balance each other out, which I think is nice. Relatively, compared to an electron, it has a big mass. Although, compared to like you or me, it has a very, very, very tiny mass. Proton is kind of interesting. A thing I could add to the electron list is that it is a fundamental particle. It means it's not made up of anything else. It's indivisible. Whereas the proton is actually divisible. It's made of quarks. I gotta spell quarks correctly. And it's made of two particular types of quarks, up and down quarks. What else? It isn't. So the proton is not a fundamental particle, although it is very important. It's one of the main building blocks of everything. And it's in the nucleus. Okay. So those are just a few of the properties of a proton. One of the interesting quarks. I gotta actually spell. Interesting thing about quarks, there are 6 types. All the matter that we interact with every day is just up and down quarks, though. So we don't need to worry about the others. They have kind of crazy names. There's up and down, there's top and bottom, and then there's charm and strange. Originally, top and bottom quarks were supposed to be called truth and beauty quarks, and I always regret, I don't know why they didn't just call them truth and beauty quarks, because they're such a weird abstract idea. I think naming them truth, beauty, charm, and strange is kind of beautiful, but who knows. We had to get top and bottom and up and down instead. And we still have charm and strange. That's okay. But quarks are these really weird guys that don't really exist on their own. If you tried to split up a proton into the quarks and gluons that it's made of, gluons are the things that hold quarks together like glue. But if you tried to split it up, the quarks would just kind of evaporate into pure energy. They can't exist without each other, which I think is kind of interesting. So in some ways, a proton is a fundamental particle because when you try to divide it, the stuff that makes it up just kind of evaporates. Kind of crazy. And the last thing is a neutron. It's in the nucleus. Put it over here underneath the proton. Neutron. It is neutral. It has no charge. Some astronomers, very quick and loose and very incorrectly, like to think about neutron as if you shoved an electron inside of a proton and just made them be super, super close friends. It's not exactly how it works, but it's kind of an interesting way to think about it. It has a big mass too. It's just a little bit more massive than the proton. It's also made of up and down quarks. In fact, it's 3 of them. They're both proton and neutron are 3 quarks each. I think, don't take my word on this because at the moment, for some reason, I can't remember quite. I think a proton is an up, a down, and another up quark, whereas a neutron is an up and then 2 downs. I think that's correct. I might have had these flipped, but I think this is correct. And it's also in the nucleus. Okay, so those are all the particles that make up, those 3 really are what make up everything, literally everything we interact with today. And in different numbers and combinations, they're responsible for everything. So, the materials that make up, myself, are just certain arrangements of protons, neutrons, and electrons. And those same protons, neutrons, and electrons are responsible for making up, I don't know, pick something, a tree outside, hot lava, the air. And one of the interesting things, the principle about these particles in particular, electrons, protons, and neutrons, is that if you take 3,000 neutrons, right, and you take your special favorite friend neutron, and you mix it up with those 3,000 ones, you could never find your special one, even if you try to mark it, because every neutron or every proton or every electron is identical to every other neutron, proton, or electron. There's no way to tell the difference between them. It's kind of a weird fundamental principle of quantum mechanics. That there's no way to tell the difference between 2 different protons, or 2 different neutrons, or 2 different electrons. They're totally interchangeable and identical. And despite that, in different arrangements, different chemical arrangements, which get very complicated, they make up the entire variety of everything we interact with every day. It's kind of crazy to think about. All right. So, that's the conclusion of what I wanted to cover today. Any questions, comments, concerns? Anyone freaking out about the fact that I mentioned quantum mechanics 3 times or 4 times or whatever? Sweet, you guys are awesome. You guys are awesome. Okay, so what I'm going to try to do is I'm going to do my best to post both the video of myself talking here. I'm going to try to clean up my notes a little bit, my type notes, because they are full of typos and kind of not very polished. And I'm also going to post these things that I drew here for you. I'm going to try to put them all up on our classroom before next class. How does that sound? All right. If there's nothing else for you guys, get going to advisory. I think it's in 10 minutes. And yeah, have a great weekend, everybody. And I'll see you on Monday.